All right, calculus students. Today we are going to finally learn how to actually get some solutions analytically to some differential equations. And the type of differential equation that we're going to learn today is probably the easiest kind, and they're known as separable equations. So what does this phrase separable mean? Well, whenever I talk about a differential equation and I say it's a separable differential equation, I mean what it looks like is that it's of the form y prime equal to some crazy formula of x's multiplied by some other crazy formula of y's. So it's really important that you've got just something with x's here, and then it's multiplied, not anything else, not add or subtract anything, another formula of y's. And this formula of x's only has x's, no y's, and this formula of y's only has y's and not x's. So that's what we mean by a separable differential equation. Y prime equals some formula of x's times some formula of y's. Well, why is that called separable? And why is it so important? Well, it turns out these are a cinch to solve. So when I say solve, I mean find an equation for y that would match this differential equation. So to see why, let me actually come up with an expression for this. So how about whatever the formula of x is, we'll just call it f of x. And whatever the formula of y's happens to be, I'll just call that g of y. And over here for the y prime, let me go back to the older notation we used for y prime, which was dy dx, dy on top, dx on the bottom. So it turns out there's a nice little way to kind of convert this into something that we know how to solve for y with. So bear with me for a moment, and then I'll justify it in a minute. So what we're going to do is, even though this is just a symbol for the derivative, it doesn't actually mean dy divided by dx, let's just pretend for a minute this is actually is a fraction here. And what I'm going to do is, and I'll justify doing this in a minute, but let's take this formula of y's and divide it on both sides. Now there's a little bit of an issue if it turns out there is a spot where this formula is 0. That's something that can be worked around, but for now let's just kind of get the general idea of what's going on. So let's take this gy and divide it out over to the other side, like so. And let's also take the dx and move that over, multiply that over to the other side, like so. Now, I just want to point out that as it stands right now, since I've separated this dy dx, theoretically this doesn't really make any sense. It's like this weird differential form, right? I mean, dy is like this weird differential, basically 0. It's like the y height of a point. So in a sense, this doesn't really make any sense. It made sense before when we had dy over dx. That was a ratio of differentials. That was actually a derivative. It's kind of like saying 0 over 0. But this by itself kind of doesn't make any sense. A dy or dx by itself really only makes sense in the context of an integral. Again, I'll justify this in a moment, but since it only makes sense in the context of an integral, what if we were just to take this weirdo equation, which doesn't really make sense, and stick integral signs in front? So basically integrating both sides of an equality. Now at least this makes sense. We haven't justified this actually works yet, but from a nice mnemonic, it kind of looks like you were just doing cross multiplication. You had dy dx equals some formula, you divided the y's over here, multiplied the x over here, integrated both sides, you end up with this. And it turns out this right here is in fact an answer to the original differential equation. You might say, wait, this doesn't look like an answer. But remember, in an actual practical problem, it would be, because this right here is a formula of y's equal to a formula of x's, like after you do the integrals, and that's just an implicit form of some solution. Now, it might be that you can get lucky and actually solve explicitly for y, but even if you can't, this is still okay, right? This is a formula of y's equals a formula of x's, and my claim is that defines a solution to this. Well, why does this procedure work exactly? So let me justify that this actually is a solution here. So the way I'm going to do that is I'm just going to take the derivative of both sides. So let me start with this side here first, because it's pretty easy to take the derivative of this. So if I'm taking the derivative with respect to x of a formula of x's, by the fundamental theorem of calculus, if I integrate the integral of f of x dx with respect to x, that's basically just f of x. Now, what am I getting on this side? Well, you might think, well, here, don't I just get like a g of y or 1 over g of y? And the answer is no, because since I integrated this side with respect to x, that means I have to integrate this side with respect to x. But keep in mind on this side, since we took the derivative of x on this side, we have to take the derivative with respect to x on this side as well. So it's not going to immediately cancel by FTC on that side. So it's the derivative with respect to x of a formula of y's. And this is like a crazy formula of y's. It's like the integral of some crazy reciprocal function g of y, where we think of y as a dependent variable dependent on x. So if we want to figure out what this is, we actually have to use the chain rule. So we're taking the derivative of some secret inside variable where everything else is in terms of y's. So that means we have to take the derivative of the outside function, the thing with the y's, but then multiply by the derivative of the inside, so the derivative of y. And we still have on the other side the f of x. So I rewrote the dy over g of y like this, so it's a little bit easier to see how to take the derivative, because now on this part we can apply FTC, because now we're taking the derivative with respect to y of a formula of y's, so the derivative of the integral are going to cancel, like so. And now we can see that if we just multiply this over to the other side, we have that y prime is equal to f of x times g of y, exactly the original equation that we had set up. So, in fact, if we solve this right here, we do get a solution to the original differential equation. So this process of separating out the y's and the x's does in fact lead to a solution. Alright, well this will actually make a lot more sense with an example. So I'll just pick a problem right here. So let's look at the differential equation y prime equals x squared y. So our goal is to get an explicit solution for this. And the first thing to notice is this is actually a separable differential equation, right? Because you got a formula of x's, in this case x squared, times a formula of y's, in this case just y. So first thing I'd like to do after I see it's separable is rewrite it like this. So instead of y prime, I write it as dy dx. And now I just imagine a cross multiplying going on. We're going to put all the y's on one side with division and then all the x's on the other side using multiplication here. So if I do that, I would have dy over y when I divide this out to the other side, and then x squared dx when I've multiplied the dx over. But you can't really write it like this, right? I mean, that's kind of the mnemonic of what's going on. But remember, this technically makes no mathematical sense, right? Because you can't have a dy by itself or dx by itself unless you're doing an integral. So let's slap an integral sign onto both those sides. So now this is what we need to solve. So, all right, what is the integral of dy over y? Bueller? Well, it's the natural log of the absolute value of y. Don't forget the absolute value. That's actually going to become important here. And this is an indefinite integral, so technically there should be a plus c after that. So all of that was the y side in red on the left. Now I got to do the x side in blue on the right-hand side here. So what's the integral of x squared? Well, we can just use the power rule on this. So add 1, divide by the new exponent. So x cubed over 3. And again, don't forget the plus c. Now, hopefully this has given you a moment of pause here, because I've intentionally made a common mistake. Because notice I wrote plus c here for this arbitrary constant, and also plus c here for this arbitrary constant. But there's nothing that says that the c that's on this side has to be the same as the c that's on this side. So it's actually a boo-boo to call them both c, right? There's nothing that says they both have to be equal. So really, that should be plus d. Now, in fact, in a minute, you're going to see that no one actually does this c and the d thing. So, because theoretically, if I was going to solve for y, what would I do? I'd want to get the y by itself, so I'd have to subtract the c over. So I'd have that. But what is d minus c? Well, don't forget what these represent. D is some arbitrary constant, 17, who knows, minus c, some arbitrary constant, 3. Well, what do you get if you subtract any arbitrary constant minus some other arbitrary constant? Well, you get an arbitrary constant. So d minus c, I could just go ahead and call that capital E, but it's traditional just to call all arbitrary constants c. So d minus c, again, the whole c is the cannibal thing. It eats other c's. So, boom, it's just one big plus c. So in reality, people don't actually write a plus c on both sides. They just kind of save themselves a little bit of time because they know they're just going to move things over and combine it into, absorbed into that constant again. So usually people just jump right from here to go right to here with a single plus c here. Theoretically, there could have been one on this side too that got eaten over, but people just write it on this side as a plus c. And we're going to see more absorbing action with the plus c in a moment. But let's finish solving this for y. So how am I going to get rid of this log? Well, the way you want to do a log is with exponentials. So I'm going to use both of these as powers on top of an e. So let's put an e down there. So raising both sides as a power to e, like that. Well, what happens here? You've got an e to the natural log of a formula, so the e and the natural log cancel each other out, and you're left with just what's inside the natural log, which in this case is absolute value of y. And this side I'm just going to keep the same, so it's e to the x cubed over 3 plus c. But we can simplify this. So let me go ahead and take this and split it up just temporarily into a product. Now that might seem a little strange that I just did that, but remember that when you multiply things of the same base, what happens to the exponents? Oh, you add these exponents together, which is why I had this. So it's just that here I started with the sum and I broke it up into two separate times. Well, why did I do that? Well, let's think about what we have here. We've got e, which is a number, 2.7 blah blah blah, raised to some constant. So this is a constant raised to a constant. Well, if you have a constant raised to a constant, that's just some arbitrary constant. So again, we get more of the c absorbing action. So all of this is like one big new constant. So again, I should call it something else, like e or d or f. But again, it's traditional, just call it c. So this entire thing, I'm going to keep the x part, because that's variables, e to the x cubed over 3. But then, rather than saying times e to the c, I'm just going to use one big c and put it out in front like that. Now, one thing to keep in mind, technically, this c isn't anything anymore. And if the point I'm about to make is about to be confusing, you can kind of ignore it because it's about to become irrelevant anyway. But I just want to point out that the c at this stage of the game has to be positive. Why does this c have to be positive? Well, remember, this c is really e to a constant, but e to the anything is always positive. So right now at this stage, this c could not be a negative number. It would have to be something positive, which incidentally also makes sense, because go back to what this is equal to. This is equal to the absolute value of something. So the absolute value of something, this had better be positive. Well, e to the anything is positive, so this c had also better be positive as well. So keep in mind this c is positive, but that restriction is about to go away, because this is the absolute value of y. But what do I really care about? What I really care about is y. So if the absolute value of something equals this, that means the thing inside is either that thing or the opposite of that thing. So in other words, if I said the absolute value, if I were to say the absolute value of y were 10, that would mean that either y was positive 10 or y was negative 10. Or in other words, y is plus or minus 10. So I'm going to do the same thing here. I'm just going to say that y is actually equal to plus or minus c e to the x cubed over 3. So I got rid of that absolute value by writing plus or minus here. But remember, c is a positive number, and now I've got a plus or minus in front of it. So the c can do more absorbing and more cannibalism, right? So this c can eat the plus or minus, and instead of being strictly positive, now can be positive or negative. So the way most people write this is just to say that this is equal to c e to the x cubed over 3. Now, technically, it's not the same c as was over there, because now it could potentially be negative, but this c, which is an arbitrary positive constant with a plus or minus in front, now becomes any constant at all, including negatives, thanks to this plus or minus. Now, if that little explanation confused you, that's okay. Think about it a little bit after the video's over and make sure it makes sense to you. But at this stage, people usually don't even bother writing these middle stages. They just go right to, after the absolute value of y equals this, they just write y equals this and pretend it's the same c and take away that bottom restriction. So really, that's your final answer. So when we started with this differential equation, y prime equals x squared y, we've now figured out that our solution is y is equal to any constant we want, positive or negative, times e to the x cubed over 3.